The most basic operation that can be performed is adding an item to the list. So let's start by seeing how to add a new item to the start of the list. It all starts with an empty list. Recall from the previous slide that a linked list is a single node chain with head and tail node pointers, both of which have initial values of null. The first step to adding a node is allocating the node. In this case, we've allocated a node with the value 3. Adding this node to the linked list means first pointing the head and tail pointers at this node. Since the list has only one item, the head and tail pointers will both refer to that same item. Now the linked list has a node to start the rest of the chain. Adding a second node is basically the same operation. We allocate a new node and point the head node to it, pointing its next pointer to the node that was previously the head node. Since we're adding a node to the start of the list, we don't need to update the tail pointer. It already points to the last node. Let's look at the code for this method. The very first thing we do is store off the head pointer into a temporary variable. It's the start of the existing node chain, and we'll want to keep our reference to that. The list's head pointer is now updated to point at the node being added to the front of the list. And the existing node chain, the temporary variable, is then linked to the new head node. We then do a little bookkeeping to track the number of nodes in the list, and if there's only one node in the list, we set the tail node to be equal to the head node, just as we did during the demonstration. As you can see, this is a very efficient operation. Adding a new node to the front of the list only involved allocating the data and updating a few pointers. The complexity or performance of this operation remains constant regardless of how many nodes are in the list. Now, if we were using an array instead of a linked list, adding to the front would involve shifting all of the existing data to the right. And if the array were full, it would involve allocating an entirely new array, a larger array, and copying all of the data from the smaller array to the larger one. This characteristic of efficient insertion is one of the key benefits of the linked list data structure. We just saw how to add a node to the start of the list, but it can be just as useful to add a node to the end of the list. Like before, we have an empty list with a null head and tail pointers. And it's that tail pointer that's going to make this operation much easier. When we create our first node, like before, the head pointer is updated to point to the new node, and so is the tail pointer. Now when a second node is created, the head pointer remains unchanged, and the tail pointer points to the new node. Having the tail pointer allows us to add the node to the tail very easily. It could certainly have been done without a tail pointer, but not nearly as easily or with such predictable performance characteristics. Let's see the code for this operation. There are only two cases we need to worry about: whether we're adding a node to an empty list or to an existing node chain. If the list is empty, we point the list head pointer to the node being added. If the list is not empty, we chain the node being added to the end of the existing chain. In either case, the tail pointer should now point to our added node, and we can increment the counter, which is keeping track of how many nodes are in the list.